So before anything else, let me introduce to the topical workbook for computer science 2210 or 0478. This is the workbook 1 for paper 1, basically computer systems. And as you can see from the table of contents, I've included questions on each and every subtopic from the syllabus along with the mark scheme. And these are some of the actual questions, actual pages as a preview from the workbook. Section 1.1, 1.3, 2.2, 3.2, 5.3 cybersecurity and artificial intelligence. This is just to show you a glimpse of what type of questions are included in the workbook. There are many more questions where these come from, and around 18 to 20 questions on an average are included for each and every topic. A must buy if you want to boost your grade. Similar to the paper 1 workbook, I have designed a paper workbook for paper 2 as well. This is for algorithm, programming and logic for CIEs either 2210 or 0478 GCE or IGCSE Computer Science. As you can see, it contains questions on every subsection of the syllabus content for paper 2 along with the mark scheme, so you can understand each and every question, each and every algorithm. These are some of the few pages from the workbook just to give you a glimpse of what type of questions are included. As you can see, this is 7.1, this is 7.7, 8.3 and section 10 Boolean logic. So a lot more questions are included in the workbook. A must buy if you want to have a very good score in your Cambridge examination. Order now.
Assalamualaikum warahmatullahi wabarakatuh. Welcome to another physics lecture. Today we would be starting section 6.2, that is the stars and the universe. The first thing we would be studying in this section is how to describe our sun as a star, or what things you should know about the sun as a star. The sun is the star at the heart or at the center of our solar system. Its gravity holds the solar system together, keeping everything from the biggest planets to the smallest bit of debris in its orbit. If the sun was not in the center, or if the sun did not possess enough gravity, our solar system would have fallen apart long time ago. According to the size comparison between different stars available in our universe, the sun is only a medium-sized star, and yet it has a radius of about 700,000 kilometers. There are stars which are much more times larger than our sun available in the universe, so our sun is considered a medium-sized yellow star. The sun formed about 4.6 billion years ago in a giant spinning cloud of gas and dust that is called a solar nebula. Sun is a little less than halfway through its lifetime, and scientists have estimated that the sun would last about another 5 billion years. The sun is a huge ball of hydrogen and helium held together by its own gravity. In fact, all these stars are technically held together by their own gravity. If they would not possess so much immense amount of gravity, they would fall apart. The radiant energy it emits is mostly in infrared, visible and ultraviolet regions of the electromagnetic spectrum. This radiation is emitted from glowing hydrogen, which is heated by the energy released in nuclear reactions within the sun. Nuclear reactions in stars. Now these reactions are not just limited to our sun, they would occur in almost each and every star across the universe. Stars use nuclear reactions to generate energy, and they give it off mainly in form of heat and light. Stable stars such as sun have a core temperature and mass which is sufficient enough for a fusion reaction to occur. And how did this fusion reaction work? All of the hydrogen atoms in the star, they start to combine together, or they fuse together in order to form heavier element helium, and this gives out a ton of energy. The high temperature required to perform this fusion is maintained by the huge energy released in the fusion process, thus causing a chain reaction, a chain fusion reaction, about which we learned in our section 5 as well. Some of the energy generated in the core is transferred to the outer layers of star, and from there it is released out to the universe or the neighboring planets and bodies, etc. The outer layers are cooler and less dense than the core, but they are still hot enough for the hydrogen gas to become superheated because it starts to glow and it emits electromagnetic radiation into space. A sun's color and brightness depends on the surface temperature, which increases with the mass of the star. The more mass a star would have, the more fuel it would have to burn, and thus the intense would be its color and its brightness. Stars that are white or blue are hotter and brighter than those that are red or yellow. Stars. Astonishingly, when we are in this topic, the topic stars, what we start about is not from how a star is born, but rather what exactly is a galaxy. A galaxy is a huge collection of gas, dust, and billions of stars, as well as their own planetary systems. You may refer to them as a solar system of a star, though technically that would be kind of correct, because not incorrect, because not every star is named as the sun. So solar system would rather refer to the planetary system of our sun. However, there are multiple stars in the universe, billions and billions of them, in fact countless of them, who have their own planets and who have their own stable planetary orbits, and those planets have their moons as well, which are revolving around their planets, and those planets are then revolving around their stars, just like our planet revolves around our sun. And some of those planetary systems have lesser planets than our solar system, some have more planets, etc. An interesting fact is we have actually identified a lot of planets which are known as super Earths. And why are they known as super Earths? Because they are situated, or their orbit is at an ideal distance from their own sun or from their own star. Hence there is a very good possibility for life thriving over there, just like it thrived on our planet Earth. Hence they are known as super Earths. Now this was just a fun fact. You don't really need to know that for your physics paper. Anyways, all of these stars and their system, as well as the whole galaxy that consists of countless stars, all of them are being held together in their respective positions by the force of gravity. Our solar system is a small part of a galaxy that's named as the Milky Way. And if you have a very clear night sky, you would see a sort of a line or a pathway made up of bright white stars, which is a visible part from our Earth of the same Milky Way. Some scientists think that there could be as many as 100 billion galaxies in the universe, but then again, nobody has actually traveled across the universe, so this is just an estimate. The now different galaxies have different shapes, and our Milky Way, like the galaxy in which we reside, is shaped like a spiral. The Sun is located in the Milky Way galaxy in a spiral arm, in one of the spiral arms of our galaxy, and that arm is known as the Orion Super. Here we are somewhere over here, and this is the shape of our rotating, spinning spiral galaxy, which is known as the Milky Way. And usually when on a very clear night, when we are having a very clear sky, the pathway of stars that we can see sometimes is actually the center part of the galaxy. The ancient people, they used to think that someone has spilled a container of milk, forming a white pathway on the sky, hence they named it as a Milky Way. Again, a little fun fact. The Sun is the closest star to Earth. Other stars that make up the Milky Way are very much further away from Earth. The nearest one, Proxima Centauri star system, which consists of 3 stars, is about 4.2 light years away. That may not sound very far away, but once you realize what a light year is, that it would change. In astronomical units, the distance that light travels in 1 year is called a light year. Light traveling in a vacuum moves at a velocity of 186 to 82 miles per second, or 299,792,458 meters per second. But the astronomical distances, or the distances in universe between stars and other objects, is so great that if you want to quote it in kilometers, you'll have a very big number. Hence, for universal distances, we don't use the term meter or kilometer. That's the SI unit for distance. We rather go for a term, for a unit that is known as light year, and light year is equivalent to the number of kilometers that would be traveled by a ray of light in 1 whole year. That would be something like 5.88 trillion miles, or 9.46 trillion kilometers. That would require that would be a very big number. So when you are saying that Proxima Centauri is about 4.2 light years away, that means the light from Proxima Centauri would take approximately 4.2 years to reach our planet Earth, and that is 9.46 multiplied by 4.2 times. That would be something like 39.73 trillion kilometers away. It is such a huge distance that it's just not possible for us to travel right now. Yes, in science fiction movies we can use a fictional device known as the opening that's mostly referred to as a warp drive, which can take you instantly from one point in space to another point in space, but we don't really have that in real life right now. So for us, this is a very big, very huge distance, and this is just the nearest star to us. I mean, apart from the Sun, others are very much further away. Life cycle of a star. The first stage is the birth of a star, and stars usually start off as an enormous cloud of gas and dust, which are many light years across. And these dust clouds, they are scattered across our universe, and they are known as nebulas. Gravity, always trying to pull everything together, starts to work over there, and it tries to pull the material, the dust and the gases, and it tries to hold them together as close as possible, and this eventually ends up in creating a giant ball of dust and gas, which is known as a protostar, which is the very first form of an actual star. As the mass increases, because that ball keeps on gathering more material, the temperature at the core due to all the gas and dust bumping into each other, which causes friction, and it causes this star to gain heat energy, as well as the great pressure of the surrounding material. It makes the temperature reach about 15 million degrees, or a little bit less or more. At that temperature, nuclear fusion finally kicks off, and the ball of gas and dust starts to glow, forming a young stable star. New stars come in a variety of size and colors, ranging from blue to red, from less than half the size of our sun to about 20 times the sun's size. But then again, this is not an exact measure. There can be stars greater than 20 times our sun as well. The color of the star depends on the surface temperature, which again depends upon how much gas and dust or how much material were collected during the formation of a star, or before a star became protostar. The more mass a star starts out with, the brighter and hotter it will be. The much larger would be its size. Next, we have the beginning of the end. That's technically the second stage in the life cycle of a star. After millions to billions of years, stars eventually start to run out of their main fuel, that is hydrogen. Once the hydrogen in the core is gone, nuclear processes occurring in a star would cease, because if there is no more hydrogen to combine, the fusion reaction cannot continue. Without the outward pressure generated in the core of the star from these reactions to counteract the force of gravity, the outer layers of the star begin to collapse inward, because now there is no balance of force. Gravity is trying to pull everything in, but to counter it, there is no outward force in form of fusion reactions that is keeping the star's outer layer stable. Hence, the star starts to contract, and when the material contracts, the temperature and pressure increase, which pushes the outer layer of the star again. This causes the star to temporarily expand to much more larger than it originally was throughout its lifetime, and it can get as much as 100 times bigger than its original size, and at that point the star is known as a red giant or a red supergiant. After a star has become a red giant, its last stage starts, and depending upon the mass, the initial mass of a star, like how much mass it was able to gather during its protostar stage, the next step of life cycle of a star varies greatly. The fate of a sun-sized star: once a medium-sized star such as our sun has reached the red giant phase, the outer layers continue to expand and the core contracts inward. Helium atoms in the core continue to fuse together under the immense pressure and heat, and turning into carbon atoms. This fusion releases a lot of energy, and the star gets a temporary reprieve. It starts to glow again and emit heat again, but this stage is only short-lived, and for a medium star it lasts for only a few minutes, not more than that. The atomic structure of carbon is too strong to be further compressed, hence the core starts to stabilize as no further reactions are possible. The star will now begin to shed its outer layer as a diffuse cloud called the planetary nebula, because that nebula, that dust and material cloud which would be spewed out by a star, would eventually become the founding material for new planets and new stars. So this is mostly known as a planetary nebula. Only about 20% of the star's initial mass remains, and the star spends the rest of its old age cooling off and emitting whatever the last of heat it has out into the space. until eventually it has no more heat and energy left, and it turns into a white dwarf with only a few thousand with its diameter being only a few thousand miles. White dwarfs are stable because the inward pull of gravity is balanced by the electrons in the core of the star, the carbon atoms repulsing each other. With no fuel left to burn, the hot star radiates its remaining heat for billions of years, and in the end it would just sit in the space as a cold dark mass, which is sometimes referred to as a black dwarf. So our sun-sized stars usually turn into white dwarf, and eventually they emit out all of their heat and become a black dwarf. For massive stars, which are 5 or more times as massive as our sun, they follow a different route. After the outer layer of the stars have swollen into a red supergiant, the core begins to yield to gravity and starts to shrink. As it shrinks, it grows hotter and denser, and a new series of nuclear reactions begins, temporarily halting the collapse of the core. However, when the core becomes essentially just iron, then it again has nothing to fuse together, because iron does not permit its atom to fuse into heavier elements. Hence, the fusion reaction ceases. The core temperature rises to over 100 billion degrees as the iron atoms are crushed together. This repulsive force overcomes the force of gravity, and the core recoils out from the heart of the star in a very what I should describe it as a very beautiful, very pretty and a very explosive shock wave. It's literally, the star bursts out. It looks just like a very pretty firework. As the shock encounters material in star's outer layer, the material is heated, fusing to form new elements and radioactive isotopes. And in one of the most spectacular events in the universe, the shock propels the material away from the star in a tremendous explosion known as the supernova, spewing off material into interstellar space. This nebula may form new stars with orbiting planets. Unlike in small stars, the intense pressure inside the supergiant causes the electrons to be forced inside of or combined with protons, forming neutrons. The whole core of the star becomes nothing but a dense ball of neutrons. It is possible that this core would remain intact after the supernova, and only the outer layers of the stars would burst out, and at that stage it is called the neutron star, because it's literally composed of just neutrons. At this point, sometimes what happens that if the star was too massive to begin with, let's say 15 or 20 times more massive than our sun, even the neutrons will not be able to survive the core collapse, and a black hole will form. A white or black dwarf is a typical white dwarf is half the mass of the sun, yet only slightly bigger than the earth, because everything is compressed together. This makes white dwarf one of the densest form of matter. White dwarfs have no way to keep themselves hot, as no reaction can occur. Therefore, they eventually cool down over billions of years, turning into a black dwarf. And a black dwarf does not radiate anything at all. A neutron star is about 10 miles in diameter, and have about 1.4 times the mass of our sun. And they spin very, very, very rapidly. Sometimes one rotation takes only mere seconds. They are the densest known object and possess gravity 300,000 times that of Earth. Neutron stars spew out fast-moving electrons, which release some of their kinetic energy in the form of X-rays and gamma rays. External viewers see these pulses of radiation at the same rate as the rotation of the neutron star, and those neutron stars which would emit such pulses of X-rays and gamma rays, they are also known as pulsars. Black holes are objects so dense that not even light can escape. The evidence of black hole comes not from seeing the black hole itself, as even light bends across a black hole, or even light cannot escape a black hole, so we cannot directly see a black hole. We can only sense it by observing the behavior of stars and other materials such as light waves around them. And over here is an image to illustrate the life cycle of a star. A sun-like star, it is formed in a star forming nebula, and then it becomes a protostar, and then it forms a medium-sized star. Then ultimately near the end it becomes a red giant. Then it becomes a planetary nebula by blasting off, and ultimately it becomes a white dwarf, and lastly it becomes a black dwarf. Whereas from the same star forming nebula, a protostar is formed, and if it is too massive, it becomes a massive star, which becomes a red supergiant, which blasts off in form of a supernova, and then it either forms a neutron star or a pulsar, or it becomes black hole. And while it is becoming either of those things, well, okay, not exactly when it became a black hole, but if it has become a neutron star during supernova, it also spews out material which later forms another star forming nebula. Okay, so that's it for today. I'll see you guys in the next lecture, and will inshallah wind up section 6.2 as well, completing the IGCSE and O-Levels physics syllabus entirely. I hope you have understood everything. If you have any problems or queries, feel free to list them below. I'll see you guys in the next lecture. Till then, take care. Allah Hafiz.